Let's talk a little bit about this concept of generating a hash. And when we're talking about uh, information security, a hash is a one-way function, one-way mathematical function. And the concept is that through an algorithm, which is basically a process, through an algorithm, you generate a particular string of ones and zeros as output based on a certain input. And if you change the input even slightly, you should get a dramatically different pattern of ones and zeros on the output. Now, the main thing we use this concept of hashing for, there's a couple of things we use it for. One of which is during authentication or use of credit or ATM cards that require the entering of a PIN number. We don't want to send the a password across the internet or a PIN number across the internet. So we use a hashing function at the point of entry. For example, it could be an ATM machine. We hash the PIN number and send it across the uh, the internet. And on the other end, where the actual authentication takes place, we uh, take the stored PIN number and the um, same hashing function and generate a hash there compared to the hash that was received from the remote location. And if they match, obviously the person who entered the PIN number knew the correct PIN number. Now we have to be careful here with PIN numbers. They're not that long. An attacker could conceivably have the hashes, all the possible hashes of that could be generated with those few digits. So something else is added in to make it a lot more complicated and hard to guess the PIN number. But that's beyond the scope of this particular discussion. And basically the same thing happens with passwords, except there are more possible passwords. So making sure that you get a unique hash that can't be matched against something that's already been generated is not that big a deal. Let me show you what I'm talking about here. I'm going to enter my name and the word professor. For this particular hash generator, and I just found this online, I really like this one because it generates a variety of hashes. And these are all different algorithms, different processes for taking this pattern of ones and zeros and generating a unique pattern of ones and zeros on the output. So let's click calculate hashes here. Now, what I'm interested in here is I want to show you how this would be used in the real world. And I've got another generator here. And this is an MD5 hash generator. So let's go back over here and find the MD5 hash, which is this. So I'm going to copy this. And I'm going to paste it off screen here, and I'll pull it in here in a moment. So that's the MD5 password generated by this online app. Now I'm going to highlight this. Now notice I started here and I went here. You have to be careful in cases like this what exactly you're copying or what you're comparing. I'll show you why in a moment. I'm going to go back over here to the other MD5 hash generator. I'm going to paste that in there. Click on generate, and there's the number generated by this one. And if you compare this, now, except for the fact that this has been shown in uppercase and this in lowercase, um, these are the same bit pattern. Now, keep in mind here, these are in hex. So it doesn't matter here that this is a capital D and this is a lowercase d, because these were generated in hexadecimal. We'll look later on at public and private keys, and from what I've seen, they're not generated in hex. They're generated strictly as a pattern of ones and zeros, and then when you try to look at them, these ones and zeros are interpreted as ASCII characters, which is not the same thing. An uppercase A is not the same thing as a lowercase a in ASCII. Hex it is, no problem. What we've done here is we took that by name and rank in one place, generated the hash. Now I could have sent you this and the hash, and on the other end you could have run the same hashing algorithm, and the fact that you got the same hash that I sent you means that there hasn't been any changes. Now, you do have to have a mechanism to make sure that this doesn't change in transit, because if a man in the middle could take that input, generate make a change to it, make a new hash, and replace the one I sent, and you would think everything's okay. So there's got to be a mechanism to handle that situation. Now, getting back to what I was telling you before, you have to be careful what you're comparing here. Watch this. If I just hit the space bar, watch what happened. I got a dramatically different hash, and this is the one of the hallmarks of a good hashing function, and I'll put it right here. So I simply added a space to our input, and notice how much the MD5 hash changed. And that would be true of any of the hashing functions. A good hashing function, minor input leads to dramatically different output. And this is a good thing, because if a minor input generated just a simple minor difference in the output, that's something that a code breaker could use to determine how the hashing function is actually working. So this is a good thing, that a minor input change gives a dramatic change in the output. So back over to this, I'm going to put a space in there, recalculate the hashes, and we were looking at MD5, weren't we? And I think you'll find that that is the same hash we were looking at earlier. So they do match. So you have to be careful what you're comparing. For a lot of purposes, you'll be doing an entire file, and in that case, keeping up with spaces is not that big a deal, because the hashing function will take the whole file as an input and process the whole thing. Now, the difference between these different hashing functions is, well, for example, MD5 is one of the simpler ones. I personally do not consider it to be secure anymore. It's just, for demonstration purposes, it's pretty simple. The higher the number of bits generated by the hashing function, the more secure it is. For example, here's a SHA 512. So this is the same input, but simply a different hashing function. Notice how much longer the pattern is. So this is a much more secure situation. And notice this has nothing to do with these. So a longer hash takes a little longer to generate, but they're much more secure. And for applications requiring greater security, use a greater number of bits. So if you recall the book gives the qualities of a good hashing function. And among the more important ones are the fact that a minor change in input should lead to a dramatically different output. You should also not be able to take the output and get back to the input. You should also not be able to come up with another input that yields the same output. Now, here's the thing about that. Just take MD5 for example. That is a big number, yes. It's not an infinite number. There's an infinite number of possible inputs. There's a finite number of outputs. So if you try long enough, you're going to get the same output for some input if you try long enough. And this is called a collision. But with a good hashing function, you shouldn't be able to look at an output and figure out how to generate the input that would create that output. So there should be no predictability between the input and the output. So these are all properties of a good hashing function. This is covered in your textbook. So read that section carefully and think about what the properties are. And we've covered some of the uses, encrypting passwords, and PIN numbers, and verification of files that you download. This is also used in forensics. When you do a forensic copy of an evidence disk, you want to generate a hash function of each of the files and also the disk as a whole, because then you can run the same hashing function on your copy of this that you're going to be actually analyzing. And if all the hashes match up, you have a true forensic copy. There's nothing has been changed between the evidence disk, which you really don't want to work on directly, and your forensic copy of it, which is what you're going to use for your analysis. So these are all examples of what you would use the hashing or a hashing function for.